Talk of today, and that's Lin Wang, who is going to talk to us about multi-stability in intra-guild predation models.
Okay, thank you, Stacy. First of all, I would like to thank the organizers, Suan, Shui, and Jiehong, for organizing such a great event in honor for Gil. And also thank them for inviting me to give a talk here. So since the event is especially designed for Gil, I want to say something about my connection with Gil. So as Xinfu mentioned on Tuesday, he has a good connection with Gil. Probably the very first person benefited from this good connection is me. So in 2003, I think it's sometime in March, when I was in the office, one of my office mates called me, "Oh, you had a phone call, and it's a lady." During my 3-year study at Memorial University, I never got a phone call from a lady. I was so nervous, and then I picked up the phone, and he said, "Oh, here come to Gil's voice." I heard it, and she said, "Okay, I can offer you a postdoc position. Are you interested?" I said, "Of course." That's the most sweetest voice I ever heard from a lady. And then soon I finished my PhD and joined Gil in September. And my master, I think I met Junior Reno, Cornell, Junyi Ma, and also Guihong Fan and Daihai He. That was a big group over there at that time. I enjoyed my 2-year stay at McMaster very much. Under Gil's supervision, I learned how to do research. I mean, we're starting working on population dynamics. And once Gil told me, if you finish the paper, don't rush to submit. Hide it in the locker for about 6 months. 6 months. After that, take it out and suppose you are the reviewer and try to criticize. And Gil also taught me how to review a paper. I remember one time, Suan asked Gil to review a paper, and then Gil gave to me, say, okay, not only you need to criticize this paper, and also need to find the most critical idea or a fresh idea, new idea from that paper, and then try to learn something from that one, right? And also how to supervise students, deal with what kind of students. And Gil also helped my teaching, sitting in my room. It's my first time to teach at McMaster. I think I learned a lot. So I want to say thank you, Gil, for all your help. And in terms of research, okay, yeah, good. So I want to briefly mention the work done with Gil. So Gil has the ability to connect people from many years ago and many years later. The very first paper we did is finish the work done with Hua Xiaxun. I think he was a postdoc with Gil as well. And in this paper, we use this global Hall bifurcation theorem and prove the existence of an unstable periodic solution, which give us some idea how to do this transient dynamics. So because we have an unstable periodic solution and solutions with initial conditions nearby, they should follow this unstable periodic solution at least for a short time. And because it's unstable, eventually we'll approach a stable equilibrium. So we can observe this transient oscillations over there. So that's the very beginning we started working on this transient dynamics. In the second paper, we dealt with a delayed chemostat model with a non-monotone response function. And we proved that some global stability. And later on with Julian, we worked out a different way to propose a delayed logistic equation. And this paper, I think after we finished, we submitted to JTB, and within 1 week, it got accepted. And one of the reviewers even said, I could write down, put my name here, let you guys know it's a good work. I think it's Ludwig from UBC, actually, one of the reviewers. And it was cited, yesterday I checked, it's 133 times. And then later on, so I think in the year of 2005, we generalized the idea to the situation with the distributed case. So follow the Gil's suggestion, finish that and put that in the locker. But before getting 6 months, I moved to Victoria, working with the police. So never got a chance to open that locker until a few years later. Churu Ning and joined Gil as a postdoc, and then we wrapped up that. Of course, she added something else and got this paper published. And also with Tim Hall and Tyner, we finished another unfinished work with that McMaster. It's a nice experience to work with Gil and work with, keep learning from her and how to get that group members get together, work together, and promote each other. So again, thank you. In this talk, I want to briefly, talk about this phenomenon of multistability in intra-Grid predation models. So I'm not going to talk about too many theorems, but instead just a common phenomenon we observed in those IGP models. So meaning we have five models. And before we do that, actually we already see something about this predator-prey competition models. I want to mention, besides the two fundamental relationships, the predator-prey relation and the competition relation, there's another one called intra-Grid predation. So which is described by this diagram here. So we have the resource, and above that we have two species. One we call the IG predator, another one is called IG prey. So on one hand side, is IG predator and IG prey, they compete for the same resource. So they have the competition. On the other hand side, they have this predator-prey relationship because IG predator preys on IG prey. Okay, so this forms a food web. The problem is this is the simplest food web model, involves 3 species, but both competition and predator-prey. Of course, this work was motivated by INSERC strategic grant led by a scientist in biology. So that's we were interested in the ecosystems in the Bay of Fundy. Over there, we have 3 key species. One is called diatoms, and then this chlorophyll, and then mud snails. The interactions between the 3 major species actually is IGP because the both feed on diatoms, and the snails that just moving around. Whenever they see the chlorophyll, they try to kill them, and so that's the IGP relationship. The general model to describe that interaction between the 3 species is this called by this model proposed by Hall and Paulis. So here R represent this resource. N is called the density of the IG prey. P is the IG predator. Okay, so you can see for R's equation, the rate of change for the R population depends on the birth and death process, BR, and this term is a consumption from IG prey. It could be a function of R, A, and P in general. And here, it's a consumption by the IG predator, okay? So for N here, it's the growth coming from consuming R, and then the consumption by P, and then this death term. So for P here, it's the consumption growth due to the consumption of R, and growth due to the consuming of N here. So here we have F1, F2, F3. This is called a functional response functions. And G1, G2, and G3 are the numerical response functions. And D1 and DP could be density dependent depth term. Of course, based on this, under this general framework, there's some other research done by a bunch of people. For example, Hall and Polis in 1997 considers a bilinear functional response. And then later on, Tanebi and Medba, and also Xu and Ran, I guess Shugui and Yang, that had a paper as well for this IGP model. That's, I think it's an ODE model. And then also Ying Kuang and her master student, I think, had a paper with the Horn type 3 function response and also specialized and generalized functional, I think it's a predation term. So Yamaguchi and his collaborators had a genetic model. Of course, there are many others, but this one is just up to, I just named quite a few here. So let's consider a very first model. We consider a two-dimensional model. Here I have X and Y. So X represents the resource population density. Of course, here we non-dimensionalized. And Y is algebraic population. Z here, I'm going to put this Z, regard this Z as a constant. The reason is that because at one season in the Bay Fungi, the snails, the number of snails actually during one season, you kind of think of that as a constant, okay? So we end up with a two-dimensional system. I want to see if we place a different number of snails in that particular region or patch, we see what's going to happen. And so here, this non-dimensionalized system, and we'll have this, if there's a new algebraic and algebraic data, we have the logistic equation, right? And here we use this Horn type 2 functional response. And here Z is a constant. I want to point out here that the one thing is this here beta 3. That's fine, yeah, that's a consumption right? From Z, but put Z as a constant. For this two-dimensional model, it's easy to do the analysis and find what possible equilibria and their stabilities, right? And we, it's not, I'm not going to put the theorems there, but this analysis of this 2D model gives us some kind of multi-stability. There are two types. One is called bistability, another called the tri-stability. So for bistability, we also observed two types. One is called we say, I say node-node, means we have one stable equilibrium that coexists with another stable equilibrium. The second type is called a node cycle. So that means it's there's a one stable equilibrium, and another one is a stable limited cycle or stable periodic solution. And tri-stability here, we observe two types. One, of course, we have three stable equilibria, and another one, we have two stable equilibria and one stable limited cycle. Okay, so that's a bistability and a tri-stability. Okay. If we have observed this multi-stability, so one thing that's the Q, that means multi-stability means the outcome is going to be initial condition dependent. So the key issue is how to find the basis of attraction for each attractor, right? So basically this involves the analysis for the stable manifold, the unstable manifold of a set point. That's going to be hard, right? So here I want to briefly introduce some numerical result. Actually, we had some Poincare map analysis, but here I just want to mention this numerical result here. So let's say an example to demonstrate the basis of attraction for the node cycle bistability. So in this green region, if initial condition is placed in this green region, the solutions will approach the equilibrium as called EBU. It's a boundary equilibrium. Basically, that means the resource will be stable and the algebraic will die out. If the initial condition happens to be inside this pink region, we have this stable limited cycle, where solutions will approach the stable periodic solution around this positive equilibrium. Okay. So the basins of attraction of the two attractors is separated by this stable manifold at a set point. Okay. An interesting thing here we found is this. The Z population we regard as a constant, which plays a crucial role to determine the basins of attraction, by which I'm going to use this diagram to show you this. So here you can see if Z is smaller than that critical value, and we see we have them 1, 2, 3, 4, 5 equilibria, and of which 2 are stable. And the blue region converges to this equilibrium, and the green region will approach this boundary equilibrium. And the interesting thing is this part. This interior equilibrium is unstable spiral. And around this neighborhood, you can see the solution could approach E0 or approach EBU. Really depends on the initial conditions. So this is a situation. So basically, I say here the basin boundary. So basically, the separatrix consists of 2 parts. One is a heterokinetic orbit from the unstable spiral interior equilibrium to the 2 set points. One is EBI, another one is EBU here. So this equilibrium here and this equilibrium here. Their stable manifold separates the 2 basins of attraction. And now you can see if at the character point, the boundary changes like that. So when I change the Z value, the number of equilibrium points never change. The stability of those equilibrium points stay the same. The only thing that changes is the basin of attraction. Okay. And if we increase this ZC here, Z bigger than ZC, you can see it's totally different. Now it is the stable manifold of this boundary equilibrium point that separates the 2 basins of attraction. Okay. So understanding this type of, we call this was a kind of a bifurcation, but that's a bifurcation. It's very different from equilibrium point bifurcation or Hall bifurcation. Just talking about the basin of attractions. So that's our first 2-dimensional model. And then later on, Xu Hu, who was a PhD student of mine, and he, of course, 2-dimensional model say it's just a training. So it's just the very beginning. So he said, okay, I should work on that 3-dimensional. So he started working on this 3D model. So I want pretty much the same, except for here. Z here not a constant anymore. And in fact, we consider this Hawking type 2 growth for this, that's consumption from Z, okay, this growth term. Here you can say if beta 2 is 0, that means the growth term here, the numerical response is proportional to the functional response. But if beta 2 is bigger than 0, that means the numerical response, the part coming from consuming X is different from the consumption. Not proportional anymore. And this part, of course, we assume still use that proportion. So basically, the key important parameters would be alpha 2 and beta 2. If alpha 2 is 0, that means we have a food chain model, not an IGP model. If beta 2 is 0, that means numerical response functions are simply proportional to functional response function. That's most research, or most papers assume that, but our collaborator in biology department, she said no, probably numerical functional response are never going to be a function of, never going to be proportional to the functional response. But anyway, we give this a try to see if beta 2 is bigger than 0, what's going to happen. Okay, so we found that dynamics actually can be summarized by this bifurcation diagram. Here, this is a case where beta 2 is bigger than 0, and I use the alpha 2 as the bifurcation parameter. And as you can see, as alpha 2 changes from 0 to a positive number, very rich dynamic is going to happen. It's going to occur. So first of all, you can see whenever we have a dashed curve here, that means we have an unstable equilibrium. A solid curve means we have a stable equilibrium. And you can see we have the boundary equilibrium. And the interesting thing here, the first critical parameter alpha Sn represent this is the side-node verification value. So when alpha 2 is at that point, we have side-node verification. When alpha 2 is bigger than this critical value, we have 2 positive equilibria. And both of them here are actually unstable. And along that branch, we have a Hall bifurcation value here and a Hall bifurcation here. That means we are going to have a limited cycle along this branch, and here basically, and these two, basically you can see observe 2 limit cycles, and these 2 limit cycles will become 1 at this point, alpha LC. That means you can think of that as a side-node verification value of a limit cycle. And beyond that critical value, there's no limit cycle anymore. And between this alpha LC and alpha H1, H2, we have a bunch of other bifurcations. One of them here is called the, you can think of that the Hall bifurcation of a limit cycle. So basically you have a home canonical orbit, and over this window, you are going to have chaos, a very rich dynamics. Okay. And the thing I want to point out here is this model could involve exhibit this biased image. So this biased image, so we have one extra type. So besides the node type biased image and node cycle biased image, we have another one is called a node torus biased image. So it means one, we have a stable equilibrium. Another, on the other hand, we have another stable solution, which actually is a torus. And this, we also have this tri-stability. So this example here shows us we have this node torus tri-stability. So if I pick 3 different sets of initial conditions, for one set initial condition, the solution approaches a stable equilibrium. For another set of initial condition, the solution approaches another stable equilibrium. But if we pick a different initial condition here, the solution is going to approach a torus. So this this torus here, actually, you can see this means if we see the non-term, you're going to see not a periodic solution, but we have oscillations. It's not chaos. So it's somehow called it a torus. So, and then I'd like to challenge him a little bit. So I say, okay, probably should work on a delayed model. So he did give it a try, and then consider a delay model. So the reason we do that is that because when we have the predictor pre-model, if we add a delay on, then the predictor pre is going to have model is going to have a Hall bifurcation. You are going to have a periodic solution, see oscillations. But for the competition model, as we see in many other talks, mentioned that so if you have the delay, then very likely the delay can stabilize the system. You are not going to see oscillations. So because our IGP model involves both delay, both the competition and the predictor pre, we want to say, okay, now we add a delay in to see are we still going to have a stabilization per effect or destabilization effect for the delay. So that's our starting point. And of course, our conclusion is that the delay is going to produce this so-called stability switch. Sometimes it can stabilize the system, sometimes it can destabilize the system. Okay, so the thing I want to put. Yes. Yes. Yeah. That's something I'm going to do the future work. That's hard, but still we one of my current visiting PhD is doing that. We still have this very complicated bifurcation, but it's not that easy to analyze because the coefficient is delay dependent. But I think we found this Hall bifurcation and also this double Hall bifurcation and other bifurcations. So I want to mention here for this system, we want to mention that biastability and the tri-stability as well. So One bistability we found is same as before. There's a node bistability. That means you have two stable equilibrium that coexist. And also we have this node cycle bistability. But here I want to point out this node cycle bistability here means we have a stable equilibrium and a stable periodic solution, but that stable periodic solution is two-dimensional. So one component is 0. But besides that, we have this cycle bistability. Okay, so that means we have two stable periodic solutions. And that's coming from, let's numerically illustrate this thing here. So you can see here this equilibrium and this equilibrium both are stable. The initial condition would be depend on will determine the final state. So it depends on what initial condition you have. So each is possible. So this bistability actually phenomena can provide us some insight to management. So okay, if I want to reserve or keep that certain species, I should do something management to change the initial condition so that the solution will switch from attracting to one equilibrium to the Bayesian attraction of another stable attractor. Okay. So that's node cycle bistability I mentioned. So that's the stable limit cycle is in the XY plane. Okay. And this cycle bistability is we only observe this in denuded system here. You have two stable periodic solutions. And then we tried to figure out the Bayesian attraction of these two stable periodic solutions. It turned out it's very hard because it's a denuded system. The phase space is infinite dimensional. It's hard to do that. Right. So the other model here, actually, it's my recent PhD. She did that, consider this different functional response. Here we mentioned this BD functional response function. So it's different from the previous one. So here I assume this BD functional response. And of course, here we still use the, or assume the numerical response is proportional to the functional response here to be able to do some analysis. So this BD functional response actually has some real applications because it's really the consumption really depends on the other species as well. Because sometimes they found they say if you have more snails on the ground on this patch, they may have some kind of internal competition, right? And if the resource or the edge prey is abundant, so how you see they have some kind of a group defense can be considered here as well. But anyway, for this IGP model with the BD functional response, we also found bistability or tristability is possible here. So here I use this numerical simulations here to demonstrate. Here we have two stable equilibria, and here it's node cycle bistability. We have stable equilibrium, and I have another stable limit cycle. So again, here this limit cycle is in the XY plane. And then the last model here, we studied is so-called IGP model with the IG predispersal. So the background here, or our motivation was that actually in one patch, so I use the U1, G, and V1. So in one patch, U1 here is a resource, and G and V1 are the competitors. So in one patch, G and V1 are competing for the same resource U1. In another patch, U2, V2, W here, we have an IGP system. Okay? So basically I have two patches. One patch I have a competition model, another patch I have an IGP model, And V1 and V2, they are the same species, but different patches. The reason here is called IG pre. So because in the second patch, patch 2, the existence of the IG predator would affect the behavior of V2. That species, okay, they say, and one time they can be consumed by the IG predator. On the other hand side, because they say, okay, they have an IG predator, they observe that they try to escape, try to avoid the possible predation from this W. So this species V2 is going to move to patch 1. But in patch 1, because here I assume this V1 is not as strong as the species G, so they have because they have competition pressure in patch 1. So okay, I'm not good at competing with G, so I try to find another patch, then try to move to patch 2. So that's a movement of IG pre between the two patches. And the movement of the IG pre connects these two patches. So I get a 6D ODE model. Our original idea is, of course, we want to see how the population dynamics is going to be affected by the IG pre dispersal from this avoidance of this possible predation from this IG predator. So this somehow relate to this fear effect mentioned by Xinfu. So basically, that's not because of the consuming effect, but it's a non-consumption effect, right? And also, this model is very complicated. We had at least 16 equilibria, and their stability analysis is very, very tedious, but it's durable. So the thing I want to mention there is we have bistability and chaos as well. So the very important thing I want to mention is this here. We have this cycle bistability. So this cycle bistability is it's different from the node cycle bistability I mentioned earlier, because here the cycle here is 3-dimensional. In other words, each periodic solution is stable. So we have 2 stable periodic solutions, and all of them are positive. So not 2-dimensional anymore, it's 3-dimensional. So here, if we pick one initial condition, one set of initial condition, the solution approaches, oh, no, here is, so here it's, oh, here it's a node cycle. It's a node cycle bistability. I think I have another, didn't put the right figure here, but anyway, we found we have this cycle bistability. At the very beginning, I didn't find that. So I asked my PhD student to do this numerical simulations for the bifurcation diagram. So she did that and said, okay, if you change the initial conditions to see if I get the same bifurcation diagram, and she tried and found that 2 bifurcation diagrams are different. So we wonder what happened. So and then I found that, okay, so in the region we have 2 stable periodic solutions. So it depends on initial conditions. So sometimes from the, but of course here just a numerical result. We cannot prove analytically that system has 2 stable periodic solutions. It's too hard.
Can you draw a diagram that a figure in 3 dimensions where 2 solutions are?
Yes, we can. Yeah, we have that 3D figure. I didn't put it here, and yeah.
They're not 2 different supercritical bifurcations from 2 different equilibriums?
No.
What I expect is because you have 3 dimensions, you have the integration. So
yes.
you have one, say for example, you have one PX solution on one basis plane. You have
okay.
on another plane. You perturbate it, and these 2 is perturbate a little bit. It becomes spatial.
Yeah.
These 2
I actually mentioned to you that is this. In one patch, I have a competition model, And because there's only one resource, it can support at most one species. So there's a boundary equilibrium that's going to be stable. So there's no oscillation in that patch, in the first patch. But in the second patch, I could have a stable equilibrium. I could have a stable periodic solution. I could have chaos. If they are connected, then there are many possibilities. Yeah, so I didn't put it here because I didn't want to mention that part. And the original idea is based on the experiment by, I think, for his name, the published in Nature, they found that, okay, because of this top predator appearance in that patch, then the structure, coexisting structure will be destroyed. And only one species, so the one species is going to die out. So they want to prove that observation, and our theoretical result prove that it's true, but under some conditions. If other conditions hold, then we might have some other possible outcomes. Yeah, that's very true here. If you play something about this migration or travel rates, the dynamics could be very complicated. So the thing I want to mention here is when we do this bifurcation diagram, we should probably try several different sets of initial conditions to make sure you got the right one. So that's we found these two periodic solutions based on this numerical bifurcation diagrams. So because we found that they look different. All right, so at the end of this talk, I want to briefly mention these possible ecological implications. So as I mentioned, the phenomenon of multistability actually has some very helpful insights for the management, because they can promote this so-called alternative stable states. Okay, if one state is one stable state is the loss stability that can switch to another stable state. So we have a multistability could provide this type of states. So one is the edge pre or edge predator, only one of them is going to survive. Another one is edge pre and or edge predator that can both survive, or one of them is going to survive but with oscillation, so it's periodic solutions. And the third situation is that we can have this coexistence. So both edge pre and edge predator can coexist, and they're going to maintain at a constant level. We have a stable coexistence equilibrium. And the third situation, that means they have that coexistence but with regular oscillations, but which I mean the stable periodic solutions. And fourth case is here, we have irregular oscillations. They can still coexist, but because the irregular, we have torus or the chaos. That means if you have some stochastic effect, one of the species could die out actually. So that's ecological implications. And in terms of management, if you see, if you figure out this basin of attractions, if you want to do some intervention, so the solution will switch their terminate and the destination in the middle, change the direction, go to another stable state. So that's for the management. So this talk is based on this three papers. So this GPNG is my former PhD student. She's currently a postdoc with Wang at Alberta. And Hong Yin Shu was a postdoc with me at that time, and Xi Hu was a PhD student. And James Oldmore, I think you knew him, he's my colleague. And I want to thank the support from INSERC. And at the end of the talk, whenever I say 70, some local people say, do you mean 17? So I say happy 17th birthday to Gil. And hopefully in 80 years, we're going to celebrate your 18th birthday. And Shugui is going to organize another event. Don't forget to invite me.
Maybe next time your turn, right?
Okay, thank you very much.